Most creek walkers in upstate New York pass right over them, glittering fragments embedded in grayish rock or half buried in gravel bars. They look like clear quartz or even shards of glass, dismissed without a second glance. But under the right angle of sunlight, a sharp edge and an unexpectedly geometric form catch the eye. A naturally double-terminated crystal, flawlessly clear. It's not glass, it's not quartz. It's a Herkimer diamond, a form of quartz so uniquely structured and optically pure that collectors, cutters, and museums alike will pay thousands for a premium specimen. The shock begins with structure. Unlike most quartz that forms in clusters or points with one clear termination, Herkimer crystals are double-terminated, meaning they naturally grow with points on both ends, undisturbed by host rock pressure. This tells us something about their genesis. They form suspended within cavities or vugs in dolostone, growing freely over time without any anchoring surface. And their clarity isn't just a visual bonus, it's diagnostic. Few natural quartz crystals anywhere in the world display this level of transparency, combined with geometric precision without polishing or lab intervention. Visual luster is the first clue. Herkimer diamonds reflect light with a vitreous to slightly oily sheen, not unlike that of high-grade topaz. They often bear skeletal growth patterns, window panes, or facet-like faces that make them look, at first glance, suspiciously like cut stones. That's part of the confusion. They mimic the appearance of faceted diamonds, especially in small sizes. Add to this their high clarity, and even seasoned gem buyers have momentarily misclassified them in field photos or poorly lit cases. But what sets the stage for serious value isn't just form. It's the context. Herkimers are geologically bound to a specific region in and around Herkimer County, New York, where the Cambrian-age Little Falls dolostone holds countless microcavities. These pockets once filled with silica-rich hydrothermal fluids, which crystallized slowly in nearly undisturbed conditions. Not all cavities yield clean crystals. Many are murky, fractured, or coated with black hydrocarbon films. But a rare few emerge flawless, sharp, and gem-clear, fetching exceptional prices even in the raw. In auctions and collector circuits, size and perfection compound value quickly. A 2-inch flawless Herkimer with internal rainbows or sceptered growths can easily exceed $2,000. By contrast, even large quartz points from Brazil may only bring a fraction of that unless they possess similar optical quality. The irony, Herkimer diamonds are quartz CO2, just like any garden variety crystal. But their formation environment, aesthetic appeal, and rarity of perfect form shift their price band drastically. And yet, despite their clarity, Herkimers don't pass the tests for diamond, a crucial distinction for buyers and field diggers alike. Their thermal conductivity is low, unlike diamonds' near-instant cold spike. But before we get there, most serious diggers learn to tell them apart visually and know where to look for the first promising signs. A sharp glint on a creek might be luck, but consistent finds come from knowing the difference before you dig. At first glance, Herkimer diamonds resemble high-quality quartz points or even pieces of broken glass. But trained eyes register a set of physical cues that go beyond shine. Most notable is their optical sharpness, crisp, geometric faces that appear unnaturally flat, almost as though faceted. Unlike typical quartz with hazy sides and uneven terminations, Herkimers boast clean, symmetrical edges and often reflect a subtle rainbow shimmer due to internal strain or minuscule inclusions. Luster is the first surface-level giveaway. Where regular quartz reads as dull to vitreous under diffuse light, Herkimers exhibit a striking oily or adamantine gleam, particularly when rotated against the sun. This is not just subjective sheen. The ultra-smooth terminations scatter light in a way that mimics polished gemstones, despite never being cut. Some faces show what appear to be parallel microgrooves or record-keeper etchings, a growth artifact uncommon in most quartz but frequent in Herkimer populations. Equally diagnostic is habit, the crystal's natural shape. While many quartz clusters show uneven growth, Herkimers typically display a uniform dodecahedral habit or complex sceptered forms, where one crystal appears to crown another like a pedestal. This symmetry isn't decorative. It reflects unrestricted space during growth, a condition only met in isolated voids within dolostone. Contrast that with smoky quartz from alpine clefts or Arkansas mines, which often terminate against bedrock, leading to incomplete or distorted forms. Weight is another underappreciated clue. Herkimers feel heavier than they look. Though their composition is pure CO2, their tight lattice and minimal internal fracturing result in a dense-in-hand impression. Field diggers often develop this intuition, testing weight before washing or cleaning, as an early sort for promising specimens. Pieces with a higher glassy feel and solid heft, even when crusted, are prioritized over similarly sized but more brittle-feeling quartz fragments. Internal clarity separates museum-grade from mundane. Under magnification or even the naked eye, Herkimers may show rainbows due to internal strain, old film inclusions, or perfect gas bubbles trapped during growth. These enhydros, water or gas cavities, raise both interest and price, especially when they shift visibly under tilting. In contrast, Brazilian quartz often contains veils, fractures, or chloride inclusions, making them decorative but not collector-grade in the same sense. The misstep most diggers make is assuming that clarity alone equals value. It doesn't. A clear quartz fragment chipped from a cluster lacks the double termination, symmetry, and form fidelity of a true Herkimer. Likewise, lab-grown quartz and glass simulants, increasingly common at gem shows, can show high luster but fail on closer geometry and habit analysis. Recognizing this at a glance isn't just about beauty, it's about understanding what formed the stone and what didn't. There's a quiet logic to where Herkimers occur, a structural rhythm beneath the rolling hills of central New York that guides those who know how to read it. Unlike random scatterings, these double-terminated crystals emerge from specific conditions tied to an ancient seabed and a very specific type of bedrock, the Little Falls dolostone. Formed over 450 million years ago in a shallow Cambrian marine environment, this dolostone is neither limestone nor sandstone. It's magnesium-rich carbonate rock, and it holds the key to the Herkimer diamond phenomenon. Geologically, Herkimer quartz forms inside vugs, natural voids or cavities, that developed as organic material decayed or as fluids leached out mineral inclusions. These voids were later infiltrated by silica-rich hydrothermal fluids, which over tens of thousands of years slowly cooled and crystallized into pristine quartz. But unlike quartz veins that fracture across terrain, these cavities don't signal themselves from the surface with mineral staining or classic vein outcrops. Instead, they're embedded within dolostone layers, often with no surface clue, unless erosion or tectonic activity has exposed them. The most productive zones lie in transitional terrain, where shallow hills give way to creek-cut slopes, and where glacial overburden has been stripped back by seasonal runoff. These cuts, often no more than a meter or two deep, reveal gray, fractured dolostone faces that occasionally display cavity scars or rough indicators of voids. If you see rock layers flaking with angular fragments, and those fragments show hints of crystal crust or void imprinting, you may be on the edge of a productive layer. Some of the richest surface finds come from slump zones, areas where overburden has partially collapsed, tumbling loose dolostone blocks down short slopes. Here, water action does the slow work of exposing crystals naturally, especially after spring thaw or heavy summer storms. Creek beds that cut through these zones carry eroded material downstream, concentrating heavier pieces, including crystals in eddy zones, gravel bars, and inside bend pools. The smart digger doesn't start with a shovel, but with walking, scanning rock faces for hollow sounds, tapped with a rock hammer, or signs of breakage where crystalline voids might have once sat. Patina can help. Weathered dolostone often darkens to a tan or reddish hue, while freshly exposed vuggy areas can appear pale gray with white mineral rinds or calcite crusts. These subtle contrasts help locate untouched or underexplored sections. Mapping matters. Most known Herkimer fields, from Middleville to Fonda, sit within a 40-mile stretch where the Little Falls dolostone nears the surface. USGS maps showing bedrock exposure can give an edge, especially where road cuts, creek erosion, or old quarries have opened access. However, even within exposed dolostone, vug frequency varies dramatically. One outcrop may yield dozens of crystals in a day. The next, meters away, may be solid and sterile. It's a game of microgeology and patience. Permitted dig zones and pay-to-dig mines often give a fast track to exposed dolostone, but public land and creek beds still hold promise for those willing to interpret slope, flow direction, and weathering patterns. Because while it's true that most Herkimers come from dolostone vugs, it's surface processes, erosion, frost action, slope creep, that bring them to where the collector can see them. You wouldn't know its value at first glance. Pulled from a shallow crevice or pried from dolostone with a cold chisel, a raw Herkimer crystal can appear disappointingly dull, coated in black manganese oxide, cemented to host rock, or wrapped in stubborn clay. Many are passed over in this state, mistaken for flawed quartz or discarded as debris. But beneath that crust lies optical clarity rivaling faceted gemstones, and the key is knowing what to preserve during cleaning, and what mistakes can permanently degrade a high-value specimen. Freshly extracted Herkimers typically present in one of four conditions: encrusted in calcite, fused to dolostone, coated with manganese black rind, or completely embedded in clay. Each requires a different treatment protocol, and improper handling, especially mechanical abrasion, can dull edges or mar faces beyond recovery. Collectors who aim for resale or certification avoid any friction-based cleaning until diagnostic features have been documented. The first and safest method is a simple water soak. Letting crystals sit in distilled water for several days can soften clay and reveal partial luster, often enough to distinguish complete terminations or window faces. For clay-heavy specimens, a soft nylon brush under running water dislodges most debris without scratching. But when faced with manganese or calcite crusts, water alone won't suffice. Manganese oxides produce a matte black coating that obscures both transparency and surface features. This is where oxalic acid becomes the standard tool. Prepared in a dilute bath, about 1 tablespoon per liter of warm water, oxalic acid dissolves the black rind over 24 to 72 hours. However, it must be used with caution. Prolonged exposure can etch sensitive faces, and gloves and ventilation are mandatory due to toxicity. Experienced cleaners keep sessions short and inspect often, stopping once the underlying luster is visible. Calcite removal, common in vug-associated specimens, requires a different approach. Because calcite reacts strongly with weak acids, a diluted vinegar soak, acetic acid, is often used first. For thicker accumulations, diluted hydrochloric acid, typically 10% solution, can dissolve the calcite without harming quartz. But this comes with a warning. If used on composite pieces, quartz fused to dolostone, the acid can weaken structural stability or release fumes from carbonate interaction. Post-cleaning, a thorough water rinse and neutralization with baking soda ensure safe handling. Mechanical separation, such as using a Dremel or dental pick, is reserved only for precision work on visible junctions. Even then, one slip can scratch a termination or nick a facet-like face. Skilled mineral preparators often use microscribe tools under magnification, removing matrix while preserving full crystal symmetry. This is especially important for specimens intended for museum display or lab certification, where natural terminations and unaltered surfaces command premium. Once cleaned, subtle features begin to emerge. Growth phantoms, faint internal zoning lines that mark different stages of development. Enhydro inclusions, small fluid pockets that roll under tilting light, or hydrocarbon veils, dark wisps trapped during crystallization. These aren't flaws, they're identifiers, and in some cases, value drivers. A single enhydro can double collector interest. A sceptered growth, where one crystal forms atop another, can multiply price 5-fold. Under a 10x loop, the illusion breaks or becomes undeniable. What looked like a clear quartz point in hand suddenly resolves into a geometrically perfect specimen, or doesn't. Herkimer diamonds aren't just about shape and clarity. Their true identity emerges in the microscopic details. Double terminations without grinding, internal inclusions too structured to be artificial, and surface growth lines that speak to untouched geologic time. This is where the true separations begin, not between crystal types, but between raw material and high-grade gem specimen. First, the double termination must be complete and symmetrical. Many crystals from quartz-rich regions like Arkansas or Madagascar may show secondary terminations or incomplete points, but a true Herkimer forms entirely within a void, developing equally from both poles. Under magnification, the ends should be sharp but not abrasive, with no grind marks or polishing residue, a key distinction from cut simulants. The edge junctions where crystal faces meet are another tell. Natural Herkimers exhibit subtle rounding or stepped growth, while artificial cuts tend to have linear facet edges and unnatural symmetry. Internal structures tell more than outer form. Growth phantoms, faint, ghost-like outlines of earlier crystal stages, appear as nested hexagonal outlines or misty zones within an otherwise clear interior. These are signs of staged crystallization, a process occurring only in natural geologic environments. Fluid inclusions, sometimes called enhydros, can be seen rolling when the crystal is tilted. These pockets, usually tiny and difficult to photograph, are prized not just for rarity, but for proof of authenticity. No lab-grown quartz includes them with this randomness and optical behavior. Another indicator is rainbow birefringence. Caused by internal strain or minute structural offsets, this effect shows as shifting bands of color under direct light, not unlike oil on water, but locked inside the stone. Herkimers often display these features near the terminations or along skeletal surfaces. While not exclusive to Herkimers, the clarity with which this effect shows in high-grade specimens adds visual appeal and market interest, especially when paired with sceptered or skeletal formations. Surface texture is crucial. Herkimers often form with what appear to be micro-etched growth lines, curved or linear grooves that follow crystallographic planes. These cannot be reproduced by polishing and are sometimes only visible under oblique light or magnification. A common mistake is to assume that a shiny surface means cutting. In fact, the best Herkimers can appear glass smooth, but are entirely uncut. Their symmetry and luster formed naturally, preserved by careful extraction. Sceptered crystals, a rarity among rarities, deserve special attention. In these, an initial crystal forms, then a second grows on top of it with a slightly offset or enlarged termination, creating a crown effect. These forms are not only beautiful but nearly impossible to fake. Under the loupe, the scepter base can be seen emerging from the original core, with visible steps or zoning between the two growth phases. Prices for such specimens can easily reach into the $4,000–$6,000 range depending on size and clarity. Despite this, not all that glitters holds up under scrutiny. Some fakes are very good, and resemble Herkimers convincingly in hand. But when magnification reveals polished facets, air bubbles, not fluid inclusions, or curved flow lines in the interior, you're likely looking at glass. Others may be natural quartz that's been lightly polished to mimic Herkimer luster, a growing problem at gem shows and online marketplaces. A true Herkimer will dazzle under daylight but flinch under scientific scrutiny if it's not the real thing. That's why serious collectors and sellers don't stop at appearance. They pull out tools. A UV light, a thermal probe, a simple scale, these expose what even the most convincing eye candy cannot fake. Because while Herkimer quartz might visually imitate diamond, its physical properties diverge sharply in ways that not only confirm identity, but also help eliminate high-risk fakes like moissanite or polished glass. Manganese oxides produce a matte black coating that obscures both transparency and surface features. This is where oxalic acid becomes the standard tool. Prepared in a dilute bath, about 1 tablespoon per liter of warm water, oxalic acid dissolves the black rind over 24 to 72 hours. However, it must be used with caution. Prolonged exposure can etch sensitive faces, and gloves and ventilation are mandatory due to toxicity. Experienced cleaners keep sessions short and inspect often, stopping once the underlying luster is visible. Calcite removal, common in vug-associated specimens, requires a different approach. Because calcite reacts strongly with weak acids, a diluted vinegar soak, acetic acid, is often used first. For thicker accumulations, diluted hydrochloric acid, typically 10% solution, can dissolve the calcite without harming quartz. But this comes with a warning. If used on composite pieces, quartz fused to dolostone, the acid can weaken structural stability or release fumes from carbonate interaction. Post-cleaning, a thorough water rinse and neutralization with baking soda ensure safe handling. Mechanical separation, such as using a Dremel or dental pick, is reserved only for precision work on visible junctions. Even then, one slip can scratch a termination or nick a facet-like face. Skilled mineral preparators often use microscribe tools under magnification, removing matrix while preserving full crystal symmetry. This is especially important for specimens intended for museum display or lab certification, where natural terminations and unaltered surfaces command premium. Once cleaned, subtle features begin to emerge. Growth phantoms, faint internal zoning lines that mark different stages of development. Enhydro inclusions, small fluid pockets that roll under tilting light, or hydrocarbon veils, dark wisps trapped during crystallization. These aren't flaws, they're identifiers, and in some cases, value drivers. A single enhydro can double collector interest. A sceptered growth, where one crystal forms atop another, can multiply price 5-fold. Under a 10x loupe, the illusion breaks or becomes undeniable. What looked like a clear quartz point in hand suddenly resolves into a geometrically perfect specimen, or doesn't. Herkimer diamonds aren't just about shape and clarity. Their true identity emerges in the microscopic details. Double terminations without grinding, internal inclusions too structured to be artificial, and surface growth lines that speak to untouched geologic time. This is where the true separations begin, not between crystal types, but between raw material and high-grade gem specimen. First, the double termination must be complete and symmetrical. Many crystals from quartz-rich regions like Arkansas or Madagascar may show secondary terminations or incomplete points, but a true Herkimer forms entirely within a void, developing equally from both poles. Under magnification, the ends should be sharp but not abrasive, with no grind marks or polishing residue, a key distinction from cut simulants. The edge junctions where crystal faces meet are another tell. Natural Herkimers exhibit subtle rounding or stepped growth, while artificial cuts tend to have linear facet edges and unnatural symmetry. Internal structures tell more than outer form. Growth phantoms, faint, ghost-like outlines of earlier crystal stages, appear as nested hexagonal outlines or misty zones within an otherwise clear interior. These are signs of staged crystallization, a process occurring only in natural geologic environments. Fluid inclusions, sometimes called enhydros, can be seen rolling when the crystal is tilted. These pockets, usually tiny and difficult to photograph, are prized not just for rarity, but for proof of authenticity. No lab-grown quartz includes them with this randomness and optical behavior. Another indicator is rainbow birefringence. Caused by internal strain or minute structural offsets, this effect shows as shifting bands of color under direct light, not unlike oil on water, but locked inside the stone. Herkimers often display these features near the terminations or along skeletal surfaces. While not exclusive to Herkimers, the clarity with which this effect shows in high-grade specimens adds visual appeal and market interest, especially when paired with sceptered or skeletal formations. Surface texture is crucial. Herkimers often form with what appear to be micro-etched growth lines, curved or linear grooves that follow crystallographic planes. These cannot be reproduced by polishing and are sometimes only visible under oblique light or magnification. A common mistake is to assume that a shiny surface means cutting. In fact, the best Herkimers can appear glass smooth, but are entirely uncut. Their symmetry and luster formed naturally, preserved by careful extraction. Sceptered crystals, a rarity among rarities, deserve special attention. In these, an initial crystal forms, then a second grows on top of it with a slightly offset or enlarged termination, creating a crown effect. These forms are not only beautiful but nearly impossible to fake. Under the loupe, the scepter base can be seen emerging from the original core, with visible steps or zoning between the two growth phases. Prices for such specimens can easily reach into the $4,000–$6,000 range depending on size and clarity. Despite this, not all that glitters holds up under scrutiny. Some fakes are good, very good, and resemble Herkimers convincingly in hand. But when magnification reveals polished facets, air bubbles, not fluid inclusions, or curved flow lines in the interior, you're likely looking at glass. Others may be natural quartz that's been lightly polished to mimic Herkimer luster, a growing problem at gem shows and online marketplaces. A true Herkimer will dazzle under daylight but flinch under scientific scrutiny if it's not the real thing. That's why serious collectors and sellers don't stop at appearance. They pull out tools. A UV light, a thermal probe, a simple scale, these expose what even the most convincing eye candy cannot fake. Because while Herkimer quartz might visually imitate diamond, its physical properties diverge sharply in ways that not only confirm identity, but also help eliminate high-risk fakes like moissanite or polished glass. Every promising crystal, especially those with visible terminations or unusual features, is tagged with a basic alphanumeric code tied to a log entry. This is key not only for tracking, but for ensuring repeatability. If a site yields multiple high-grade specimens, documented orientation and depth can inform future extractions or guide fellow researchers to adjacent productive seams. In commercial digs, this data also supports royalty or claim-based disputes, where chain of custody becomes critical. A common mistake at this stage is overhandling. Herkimers, despite their hardness, 7 on Mohs, can chip along microfractures, especially near terminations. That's why raw handling involves foam trays, silica gel packets to avoid condensation, and minimal surface contact. It's not paranoia, it's preservation. It's the most frustrating scenario. A crystal with perfect geometry, stunning clarity, and bright luster, only to fail one test that shatters its story. False positives in the Herkimer world don't just waste time, they corrode trust, inflate collector losses, and muddy the trade. And the most dangerous imposters aren't clumsy fakes. They're convincing minerals with legitimate credentials that check most boxes, until the right test disqualifies them. That's why every serious collector, digger, or dealer must recognize the three main problem materials: zircon, moissanite, and high-grade glass or cut quartz. Zircon is the classic trap. Naturally double-terminated, optically clear, and occurring in small crystals, it mimics Herkimers remarkably well, especially in older river gravels or glacial tills. But zircon is heavier, much heavier, with a specific gravity of 4.6 to 4.7. That means it feels dense even in tiny samples. A quick SG test with a simple water displacement setup often unmasks zircon immediately. Additionally, under UV light, zircon may fluoresce yellow or reddish, unlike the white-blue or non-reactive profile of Herkimer quartz. When magnified, zircons show tight, stubby terminations and a high-index sparkle that feels metallic to the eye, almost too sharp. Moissanite is even trickier. As a lab-grown diamond simulant, it's often cut and polished, but some synthetic moissanite can appear raw and terminated, especially when weathered or handled poorly. Moissanite beats quartz on hardness, 9.25 versus 7, passes many diamond testers, and shows strong double refraction. The latter is your best ally. Under a loupe, look for facet doubling, ghost images along edge lines, which are absent in quartz or Herkimers. Moissanite also conducts electricity, unlike quartz. A dual-mode tester, thermal and electrical, is essential when doubt remains. Then there's cut quartz and glass, the most pervasive and subtle threat in online sales and gem shows. Polished quartz from Brazil or Madagascar is often lightly faceted or tumbled to mimic Herkimer form. Glass is even worse. High lead content, sometimes doped with rare earths to produce false rainbows or UV reaction. These fakes often slip past casual tests, especially when coated in light dust to appear natural. But telltale signs remain. Air bubbles in glass, round, isolated, and motionless, contrast with enhydros, which shift subtly under tilt. Glass also lacks growth phantoms, scepters, or natural microetching on the surface. Under oblique lighting, glass feels flat in depth. Herkimers reveal layers and texture even when internally clear. Some fakes are hybrids, quartz points glued together to simulate scepters, or clear quartz with polished tips to imitate full terminations. Under magnification, glue lines appear cloudy or show capillary haloing, tiny disturbance zones around the bond. These should be discarded or flagged immediately. Certification labs like GIA or IGI routinely detect such alterations, and any dealer unable to prove natural, unaltered growth should be questioned. Visual patterning offers one last diagnostic. Herkimer diamonds grow in dolostone voids and typically show skeletal faces, stepped growth zones, and subtle optical zoning. Fakes rarely replicate these, especially the combination. One missing element doesn't doom a specimen, but the more natural features present, the less likely it's a counterfeit. Crystals with perfect geometry, but no internal rainbows, no phantoms, no microgrowth texture. High risk. What makes this problem harder is that Herkimer-like crystals do occur in other parts of the world: Pakistan, China, even Arizona. While similar, these often differ subtly in luster, formation host, and internal clarity. True Herkimers are unique in their consistent association with Cambrian dolostone and specific inclusion patterns. That's why origin tracing, backed by field documentation, matters. When a seller can't state where or how a crystal was found, assume marketing is masking unknown provenance. Every promising crystal on the surface hints at something deeper, a pocket still intact, a seam of vugs untouched. But as soon as surface collecting gives way to targeted extraction, the risks and rewards escalate fast. Field recovery of Herkimer diamonds shifts from casual scanning to physical labor with real consequences. Fractured stones, lost terminations, or worse, collapsed walls and wasted zones. This is the stage where amateur enthusiasm can destroy a premium find or worse, create danger. Yet with the right gear and tactics, the transition from surface to source can yield museum-grade clusters and marketable specimens worth thousands. The first reality is this: Herkimer quartz doesn't grow in veins, but in isolated cavities within dolostone. Unlike gold or gem pockets that follow fracture lines or dike trends, these vugs appear randomly in blocks, sometimes just centimeters apart. That means the ideal tool isn't a pickaxe or jackhammer, but a precise strike with a crack hammer and cold chisel. The goal isn't to pulverize, but to free the dolostone surrounding a cavity intact. Blunt force creates fractures that radiate through the vug, instantly devaluing or destroying the crystals within. Serious diggers operate with a layered approach. Surface soil is cleared with flat shovels or trowels to reveal dolostone edges. At this point, tapping becomes the primary technique, using a geologist's hammer to sound for hollows. A sharp, resonant ping instead of a dull thud can signal a void beneath. That's where the chisels come in, inserted gently into existing bedding planes or natural seams, not forced. The idea is to let the rock split where it wants to, not where you demand. The most productive technique is what miners call facing, systematically removing horizontal layers of dolostone one slab at a time. This exposes cross-sections of cavities and preserves any crystal clusters within their natural growth geometry. Herkimer vugs often present as circular voids lined with crystals, but the largest pockets, skulls, as diggers call them, can be bowling ball-sized, with hundreds of points radiating inward. These must never be struck directly. Instead, surrounding matrix is chipped away until the pocket can be pried or gently collapsed inward. Flood and freeze-thaw cycles complicate this. Dolostone becomes slick and brittle when wet, and some outcrops become hazardous after heavy rain. Spring and fall are ideal. Ground moisture is low and vegetation doesn't obscure access. But even then, safety matters. Dolostone outcrops can shear unpredictably, especially near water-cut ravines. Smart collectors wear hard hats, eye protection, and gloves, not for style but survival. Crystal cuts are sharp, falling blocks are worse. Permits vary. On public land, collecting is often prohibited or heavily restricted. Private landowners near Middleville, Fonda, or Little Falls may allow digging for a fee, but require strict rules on fill replacement, tool limits, and noise. Violating these not only results in fines but risks site closures for everyone. Always check with the local DEC or land registry before digging, especially near creeks or state-managed forest tracts. When a pocket is opened, time compresses. Oxygen and moisture begin affecting delicate terminations almost immediately. Experienced diggers have foam trays, padded cloths, and mist bottles on hand to stabilize fragile crystals for transport. Any attempt to pry them out with metal tools, even tweezers, risks breakage. Some specimens are so delicate they are removed inside their host block, then lab-prepared later using microabrasive tools. The payoff, fully formed clusters with pristine points, sometimes dozens on a single matrix, that sell to collectors, institutions, and jewelry cutters. A complete pocket with enhydro-filled scepters or rainbow inclusions can sell for over $10,000, depending on size and clarity. But the cost of one careless strike is steep. Even a minor chip on a key termination can drop value by 70%. Once a crystal is out of the ground, the clock starts ticking. Not just on condition, but on provenance, the record of exactly where, how, and by whom the specimen was recovered. Without that chain of context, even the most visually stunning Herkimer risks devaluation, exclusion from reputable collections, or skepticism at sale. That's why serious field workers and professional diggers prioritize documentation as highly as the crystal itself. Because in today's market, a certificate of origin is no longer optional. It's a silent multiplier of trust and price. The gold standard begins with grid logging. For each pocket or significant find zone, coordinates, GPS, or mapped reference are tied to a labeled storage container or bag. If GPS isn't feasible due to terrain, a site sketch with distance and orientation from a fixed landmark can suffice, as long as it's repeatable. Each find receives a code, something simple like HF23A1, Herkimer Field 2023, Pocket A, Specimen 1. This links the crystal to location, extraction method, matrix context, and notes on surrounding mineral indicators. Photos are essential. Ideally, the crystal is photographed in situ, still embedded, partially revealed, or just freed from its cavity. These images carry enormous weight during verification, especially when the stone exhibits rare traits like enhydro inclusions or sceptered growth. If a buyer, lab, or museum sees clear evidence that the formation is natural and unaltered, the price ceiling rises. That documentation also deters fraud claims later, a growing problem in high-end mineral sales where lab-processed fakes are increasingly sophisticated. Storage follows tight rules. High-grade Herkimers are never jumbled. They're placed in foam-lined cases or compartmented trays with labels tied back to the field log. For matrix pieces, the host rock is never trimmed unless absolutely necessary. And even then, it's done with air scribes or diamond saws under lab conditions. Field chipping to reduce weight is one of the costliest errors a novice can make. A perfect cluster worth $2,500 can drop below $600 if trimmed improperly or without photographic proof of its original orientation. Moisture control also matters. Crystals with visible internal inclusions, especially enhydros, are kept in climate-controlled storage to prevent condensation, which can obscure clarity or, in rare cases, create expansion pressure. Silica gel packets are standard in sealed cases. For large collectors or dealers, digital inventories track each specimen with photos, test results, and market notes. Ethics enter here too. Not all Herkimers come from legally accessed land, and some dealers knowingly obscure origin to dodge fees or permits. Reputable sellers provide written assurance of land access, either through lease, claim, or dig site agreement. When you're investing in a stone that may appreciate over time, legal clarity is as important as optical clarity. A documented origin from a known productive zone, say Ace of Diamonds mine or Crystal Grove, commands more trust than an unverified upstate New York label. In the gem cutting industry, provenance affects value downstream. A cutter may pay a premium for a Herkimer known to exhibit minimal internal stress, reducing fracture risk during faceting. Likewise, metaphysical buyers, a major secondary market, place high importance on authentic energy, tied to region and handling. Though not a scientific measure, it impacts real pricing. For this reason, dealers often include field notes or story cards with sales, weaving the stone's journey into its value profile. It's not size alone that drives Herkimer value into the thousands, it's structure. Specifically, the kind of growth patterns that don't just look pretty but signal geological rarity and collection importance. While many crystals from the Herkimer region are sharp, clear, and symmetrical, only a select few display the internal and external features that elevate them into elite tiers. Flawless interiors, sceptered growths, skeletal formations, enhydro chambers, and multi-phase development. These aren't just aesthetics, they're geological signatures that form under rare, stable conditions, often over tens of thousands of years. The highest premiums go to flawless, doubly-terminated crystals exceeding 2 inches, with no internal fractures, no contact damage, and fully natural terminations. These pieces often resemble lab-grown material at first glance, which ironically boosts their value when proven authentic. 2.5-inch Herkimer with perfect optical clarity, 0 inclusions, and document in situ origin can command $3,000-$5,000 at auction, with enhydro inclusions or rare growth structures that range doubles. Sceptered Herkimers are the crown jewels of the category. A scepter forms when a second-generation crystal grows atop a terminated base, often larger and slightly offset, creating the illusion of a crown or bulbous cap. The mechanics behind this are rare. A second silica infusion after cavity formation, at slightly different pressure or temperature, allowing a new crystal to seat atop an existing one without merging boundaries. These structures are highly sought after not just for their visual drama, but for what they reveal about changing geologic conditions within the same cavity. The best scepters show distinct growth junctions under magnification, often with zoning lines, mineral inclusions, or subtle color shift marking the boundary. A Herkimer scepter with a clear cap over a smoky or carbon-filled base commands extraordinary attention. Prices for these can reach $7,000-$9,000, particularly if paired with enhydro chambers or multi-crystal clusters. And size isn't everything. Even small sceptered pieces under 1 inch can fetch over $1,000 if the form is architecturally perfect and fully terminated. Skeletal and hoppered growths add another layer. These are crystals that form faster along edges than faces, creating hollow or negative zones inside the crystal. They look like miniature architecture, stair-step, geometric voids echoing the outer form. Skeletal Herkimers often develop when fluid supply fluctuates rapidly, or when rapid cooling interrupts stable growth. Under light, these voids refract dramatically, creating complex internal reflections that enhance visual depth. Few quartz types display skeletal growth naturally, Herkimers do, and collectors pay for it. Inclusion types further stratify value. Rainbows, caused by internal strain or ultra-thin film layers, appeal to aesthetic buyers and metaphysical users alike. Hydrocarbon inclusions, dark, oil-like streaks locked within the quartz, are far rarer and increase scientific interest. The rarest inclusion of all. Active enhydros, tiny water or gas pockets that visibly move under tilt. These aren't just curiosities, they're proof of geologic fluid conditions at time of growth. High-value enhydros are fully enclosed, not surface-reaching, and large enough to view with the naked eye. Still, it's not just what's inside, it's how intact the crystal is. Chips, especially on terminations, dramatically lower price. Even a flawless scepter with a minor ding might only fetch 40% of its potential value. That's why top diggers and preparators spend hours preserving edges, cleaning with ultrasonic tools instead of abrasion, and storing specimens in vibration-proof cases. Clusters, multiple Herkimers growing in interconnected formations, can also reach top-tier pricing, especially when the crystals are all terminated, undamaged, and well-positioned on the matrix. A multi-crystal VUG plate, fully cleaned and stabilized, can exceed $10,000 depending on provenance and structure. But the risk rises too. Clusters are fragile, and even minor breakage during extraction or cleaning can destroy alignment and value. The counterfeit Herkimer isn't a future threat. It's already here, buried in the trays of gem shows, flooding online listings, and even showing up in lower-end metaphysical shops with convincing stories. The irony? These fakes often fool more than just casual buyers, because the highest-risk pieces aren't crude glass replicas. They're well-formed, high-clarity quartz crystals, real quartz, often from Brazil or China, that have been cut, polished, or chemically treated to resemble Herkimers. And without careful examination, even seasoned collectors can be taken in. The most common counterfeit is the polished double-terminated quartz. These are usually clear quartz crystals that have had their natural ends ground into sharp, symmetrical terminations, then lightly polished to enhance luster. From a distance, or in a well-lit online photo, they can appear flawless with symmetrical faces and optical clarity rivaling top Herkimers. But under a loupe, the deception breaks. Termination edges are too linear, faces too flat. Polishing leaves microscopic sweep marks or facet planing lines, absent in naturally grown Herkimers, which display subtle stepped growth or tiny dissolution patterns instead. Then there's the glued scepter, a base crystal joined with a smaller point to mimic the rare growth structure. These can be disturbingly convincing, especially when matrix or epoxy is used to mask the join. But chemical adhesives fluoresce differently under UV and often show separation halos under magnification. A simple acetone swab test on the base, if the seller allows it, can sometimes reveal bonding agents. And in high-risk specimens, X-ray or Raman spectroscopy may be needed to confirm continuity across the junction. Irradiated quartz is a subtler fraud. These stones are exposed to gamma radiation to produce unnatural smoky tones or rainbow effects. While not inherently fake, they are altered, and when sold as natural Herkimer material, it becomes deception. The key giveaways are overly uniform color zones, especially deep grays or purples with no natural zoning, and unnaturally intense rainbow bursts near terminations. Natural Herkimers with rainbows show subtle, irregular banding, not spectral flashes, concentrated at edges. Even raw glass simulants have improved. Leaded glass with high refractive index now appears in fake Herkimer lots, sometimes mixed in with genuine specimens to inflate visual appeal. These pieces often feel slightly lighter in hand, and when examined with a polariscope, may show strain patterns inconsistent with quartz. Air bubbles, round, uniform, and motionless, are another tell, as true enhydro pockets behave dynamically when the crystal is tilted. In some cases, misrepresentation isn't visual, it's locational. Sellers claim Herkimer provenance for quartz found elsewhere, especially in Pakistan, China, or the western US, where double-terminated quartz can also occur. These pieces are sometimes labeled Herkimer style or Herkimer type, but marketed ambiguously to create price justification. True Herkimer diamonds only originate from the Cambrian dolostone belt in and around Herkimer County, New York. Anything else is, at best, an imitation, at worst, a fraud. To combat this, reputable mines and dig sites like Ace of Diamonds or Crystal Grove have begun issuing site verification certificates, especially for large or premium specimens. These aren't official lab certifications, but they document when and where a stone was collected, tying it to a known geologic setting. Dealers who can provide photos of extraction, site logs, or detailed handling history stand out, and in high-dollar transactions, buyers increasingly demand it. Labs are stepping in too. GIA and other mineralogical labs can now certify quartz origin through microinclusion analysis, trace element ratios, and growth pattern studies. While costly, these reports pay off for high-end stones heading to auction or museum display. In particular, they protect against the growing influx of quartz fakes originating from overseas factories that specialize in gem simulation. But perhaps the most telling sign isn't on the stone, it's in the seller's behavior. Vague origin stories, resistance to testing, and a refusal to allow handling before sale are all red flags. So too are listings that emphasize metaphysical attributes over mineralogical data. A real Herkimer can hold both value streams, scientific and spiritual, but only one is objectively testable, and when values rise, the scrutiny must match. The transition from enthusiast to reliable producer, you need more than sharp eyes and strong tools, you need a process. Professional Herkimer diggers don't just hope for good pockets. They build grid systems, track void productivity, and follow tested recovery workflows that allow for scalable, ethical, and repeatable extraction. This isn't just for volume, it's for validation. Because the more consistent your documentation, orientation, and test routine, the more credible your stones become in market and institutional eyes. The grid starts on the ground. Before the first rock is moved, serious field teams stake out a trench or face with a rectangular overlay, often 1 meter squares, and assign each zone a code. This allows for side-by-side comparison of void frequency, crystal density, and matrix type. Over time, patterns emerge. Pockets align with thin calcite seams or occur more frequently in a certain depth band. These data points are tracked on waterproof field sheets or mobile mapping apps with offline GPS capability. The advantage: when one pocket produces, adjacent grids can be prioritized or flagged for return visits, maximizing yield and minimizing wasted effort. Orientation is critical. Crystals removed without noting their alignment to host rock lose part of their scientific and aesthetic story. For clusters, this is especially damaging. Professionals take high-resolution photos of exposed vugs before and during extraction, using scale bars and direction indicators. These images are stored with specimen logs, and often printed or included in eventual sales or museum documentation. The result is a verifiable chain from rock face to showcase, a major trust builder in both private and institutional markets. Each specimen's unique traits are cataloged the same day it's found. Beyond location and size, key fields include termination count, single, double, luster type, vitreous, silky, dull, visible inclusions, enhydro, carbon, phantom, and surface features, skeletal, hoppered, record keeper. Even fragments or partial crystals are tagged, as these can be used in future comparative testing, faceting trials, or as reference stock for inclusion analysis. To maintain consistency, a portable field station is set up, usually a folding table under tarp cover, with padded trays, sieves, cleaning basins, distilled water only in field, a 10x loop, a UV flashlight, and a basic thermal conductivity pen. The goal isn't deep testing yet, it's triage. Identify what needs protection, what's worth testing later, and what may be left in matrix for preparation under lab conditions. Ethics enter early in the process. Digging on private land without written permission isn't just illegal, it invalidates any provenance claims. That's why reputable diggers carry permit copies or lease agreements on-site and photograph the access signage for future record. Mines like Herkimer Diamond Mine and Crystal Grove provide diggers with day tags or trench designations, which can later be linked to fines. In cases of shared pockets, where multiple diggers intersect the same void, rules are clear. Whoever exposes the termination first gets first claim, but matrix pieces must be agreed upon before division. Disputes are rare when rules are followed, and catastrophic when ignored. The final layer of process is repeatability. This means returning to high-yield grids at seasonal intervals, logging changes in productivity, and rotating pressure points to allow natural erosion to continue revealing new material. Overmining is a real risk, and once a vug field is depleted, recovery takes decades. That's why top diggers often operate in cycles, alternating between 2 or 3 known productive sites while testing new zones during off-peak months.